All right, so, wow. First and foremost, I appreciate you all being here. Thank you for your time. And thank you, Ben, for hosting this great platform. I'm thrilled to be here. The plan for this morning, this afternoon, this evening, whatever time it is, wherever you may be, is to go through A320 flight control laws. I will share with you the flight control laws on the 320 are one of these things that give a lot of headache to many people. It certainly gave me a lot of headache because I transitioned from Boeing. And frankly, when I heard flight control laws, I'm like, I don't know what that means, why we need it, what does it entail, why is this installed, how does it work? And this is very specific to Airbus. So if you've never flown a bus product before, this will be effectively new to you. And there's some nuances with it, mainly with like side stick relationship, G-load versus roll rate versus direct, when do you have what, all these types of things. So with that, we're going to spend the next few hours together. If you have questions, I will do my very best to answer them. I don't have all the answers to everything, and I certainly don't profess for that to ever be the case, but I will certainly say I'll do my best to answer based on what knowledge I have, and if we can't do that, then I'll do my best to find it and deliver the answer to you. So with that being said, I think we'll get cranking here. Hi, Yvonne, Cody, what's happening? Christian, good to see you. So let's talk about laws. So first and foremost, A320 flight control laws, or laws in general. I'm going to just start with what is a law. And this was one of the things that I had trouble defining. What exactly is a law? Now, I've heard it defined several different ways. And the one way that has stuck with me, and I think is a pretty decent way of describing it, is that it's a set of rules by which flight controls are governed. It's a set of rules by which flight controls are governed. Now, those rules come from the various computers that we have, which we happen to have 7 computers that we're going to talk about, the ELAC and the SEC and the FAC, all of them. And those computers are the ones that dictate what law we're in. And so each one of these laws is going to establish a different set of protections, maybe stabilities, or maybe nothing at all. So with that said, let me get closer to the camera. We're going to break out the whiteboard, and I'm just going to start going straight down the list here. Hopefully you can see this. With the first law that everybody's familiar with, which is normal law. And there's a total of 4 laws, so we'll start with normal. And then after normal, we have alternate law. And then after alternate, of course, we have direct law. And then the last law here we have is what? What is the last law? I'm pausing for a second because a lot of times I get a response that the last law is, well, let me do something quickly. Let me check the chat here for a second. Okay. Africa's in the building. Darius, what's happening? Good to see you. Okay, so the 4th law then is abnormal attitude law. And typically, what I hear is mechanical backup. And for those of you that have watched any of my material before, you may have heard me say several times that mechanical backup is in fact not a law, but it's the absence of any law. And that has to do with because of some of the loss of some of the flight control computers that we have on board. So we're going to look at that here, but I'll put mechanical backup maybe off to the side here, and then we'll eventually talk about that later on this morning. I say morning because it's morning in Miami, whatever time it is where you're at. But normal, alternate, direct, and abnormal attitude. So let's first look at these laws here. So normal law is where we typically reside. Normal law is where we're at, assuming everything is normal. And the reality of it is that this is also the law that offers the most amount of protections. Now, in total, we have 5 protections. And for those of you going to upgrade or initial recurrent, just so you have an understanding, typically a series of questions, I've already given you several answers this morning that could come on an oral, is what is a law? How many do we have? What are they? Which one has the most protections? So we already answered a law, set of rules by which flight controls are governed. They're governed by the 7 computers. There's 4 total. These are the 4. Normal has the most amount of laws. Okay, or protections. So the first protection I'm going to list up here is G-load. Okay, and G-load protection, you're probably familiar in a clean configuration, 2.5 to -1 G. There goes my mic. And see, this is one of the technical difficulties I talked about. There we go. So with the normal law, G load protection, when we have 2.5 Gs to a minus 1 G, I just want to pause at the 2.5 G for a second and talk about why is it 2.5 G? Who came up with 2.5 Gs here? And you should know that ultimate load, which is effectively the G load where potentially things could break off the airplane, is 3.75 Gs. So they're giving us a considerable amount of margin or buffer before we ever reach anything like that. So that's your G load protection. That's assuming we're clean. And then of course, if we're dirty, it would be 2 to a 0 G, 2 to minus 0 G. So that's your G load. Beyond that, we have, of course, pitch protection. And pitch protection, as we all know, is plus 30, right, down to a minus 15. And then we have, finally, roll protection as we work our way down, 67 degrees. 67, this was another one that I thought for a while, who came up with 67? Why not make it 65 or 60 or 70 degrees of bank? Why is it a 67 degree roll protection in terms of the roll? And this basically relates back to the G load. So effectively, if you turn 67 degrees of bank and pull on the stick aft to maintain altitude, you're going to run up against the 2.5 G load limit. So the bank angle ties directly to another limitation, which happens to do with G load. So hopefully that makes sense. They both tie in. Apart from that, we have airspeed protection. And with the airspeed protection, what you want to know about this is there's two triggering events. There's VMO plus 4 and there's VMO plus 6. So plus 4 knots, we start to hear the aural alert of the overspeed, and then at plus 6, the actual overspeed protection activates its actions, one of which, of course, including the autopilot disconnecting and the nose beginning to come up in an effort to reduce airspeed. What I'm going to say about airspeed protection that's very interesting, you may or may not know this, airspeed protection is one of the few protections that you can actually, to some degree, override. It's not completely overrideable, but you very much can grab the side stick and continue to push nose down and overspeed even deeper into the airspeed tape, all the way upwards of plus 16 knots. So you can go another plus 16, at which point the side stick will gradually begin to lose authority. And you may wonder, why would it allow me to do that? Why would I ever need to go another plus 16? And the truth is, hopefully you never have to do that. But the challenge would be if you get a TCAS RA and it's in, somewhere maybe in the flight levels, and it's a descend RA, descend. So autopilot off, flight director's off, you start nosing down, you run up against the overspeed protection, which inevitably will drive the nose up. But because we have this additional plus 16 knots, it'll let you bury the nose down a little bit further in order to help in that particular scenario. So basically, Airbus did a good job, I would say, in my opinion, of installing these protections that very much work in our favor, but then also limiting them to some degree so that they don't completely overpower us and put us in a position where we can't even really put effective inputs to recover the jet, which is really why in a normal attitude law, it gets rid of all protections, which we're going to look at later on. At least temporarily it does. Anyway, so that's your airspeed protection. And then, of course, we have the alphas. We have alpha protection. So the alpha protection is basically three things, which is alpha prot, alpha max, alpha floor. And we'll start with prot, and then we'll just go down the list with max and floor. Alpha prot, what is it? What exactly is alpha prot? So alpha, let me back up and say this. Alpha is short for angle of attack, and prot is short for protection. So alpha prot effectively means angle of attack protection. This is Airbus's initiative to not necessarily put in a stick shaker or a pusher, but certainly install some remedy to help us not get dangerously close to stalling an aircraft. And so with that being said, alpha prot is the angle of attack where the flight control computers will intervene to prevent a stall. There's several ways of describing it. That's one way that I've heard described. I tend to use that and preach that in terms of a response on an oral. I think it does a good job of articulating what it is that alpha prot is, which is, again, an angle of attack where the flight control computers intervene to prevent a stall. Now, how exactly does it do that? And there's several things that it'll do, right? So the first thing it's going to do is it's going to disconnect the autopilot. And anytime we do stall recovery, or I should say approach to stall recovery in the sim, because in the sim we never do, unless you're an EET or UPRT in a type rating environment, we just do approach to stall recovery. and we recover at the first indication of a stall. And generally when we do our first stall of the stall series, the first indication is the autopilot disconnecting, which is a tall tale sign and the signaling of the fact that we're entering into alpha prot. So the autopilot disconnects. The next thing that happens is the side stick is actually now commanding AOA as opposed to G load. So we're going to look at that a little bit more. And the spoilers will stow automatically if you happen to have them out. And finally, the pitch trim in the nose up direction freezes. You can still trim nose down, which would help in the recovery of the stall, but I can't trim nose up. And so for those of you acronyms, I realize our industry is full of them, but there is an acronym, it's ASAP, that kind of more clearly articulates alpha prot and how exactly it does what it does. So the A, the first A of ASAP is autopilot disconnects. The S is the spoiler stow. The second A is angle of attack is commanded by the side stick as opposed to G load, which is technically in normal law the relationship that we have between side stick and ELAC. We will dive into that here shortly. And then finally the pitch trim freezing in the nose up direction. That's alpha prot right there in a nutshell. Now if you grab the side stick and for whatever reason you keep pulling on this thing, you're inevitably going to now go into probably alpha floor first and then later alpha max. So let's talk about alpha floor. Alpha floor is a predictive function of the autothrust system. A predictive function of the autothrust system. I'm really emphasizing, and by the way, if you see me look off camera, it's because I have a nice big screen over here where I can watch the chat and I can see who's participating. So I do appreciate you all being in here. I'm just checking in on this occasionally in case there's questions I'm missing. So alpha floor, predictive function of the autothrust system. You got to use the word predictive in any response that you're giving to an examiner. And the reason I say that is because it is what it sounds like. It very much predicts. You do not have to go in sequence. I don't have to go through alpha prot and then alpha max to get to alpha floor. Effectively, if the jet doesn't like the energy state you're in, the G loading that you're putting on it, and the energy state that you're trending towards, it's going to give you toga power, period, end of story. So alpha floor is very much a predictive function of autothrust. Now, what does it do? It commands toga power. And your FMA, or your flight mode annunciator, initially is going to read A dot floor. All right, let me get a eraser here just to clean this up for a second. So your flight mode annunciator is going to read initially A dot floor. And when it says that, what you want to know is, hey, I'm getting toga power commanded. Your engine gauges will validate this. And then the moment we reduce the angle of attack a little bit, alpha floor will give birth to something called toga lock, which means effectively what it sounds like. Toga thrust is very much locked. How do I get out of alpha floor? There's really two ways to get out of it. Really one, but different variations of it, which is to disconnect the auto thrust. And the way typically that we disconnect auto thrust, of course, is via the disconnect push button, the instinctive disconnect push button, whatever they call it that, I don't know. You hit the IDP, and when you hit the instinctive disconnect push button, it will disconnect the auto thrust. Now, there is another way to disconnect the auto thrust, which is effectively to reduce it from the active range, which would be basically back to the idle position if I bring the thrust levers back to idle. I don't particularly recommend that, only because you're in an energy state that seemed to think you needed toga power, so I probably wouldn't reduce it to idle unless you had quite an excessive energy state on your airspeed tape. So, but certainly disconnecting the auto thrust will get you out of that. Now, for you to have alpha floor, you got to have auto thrust available. Available. Listen to the word choice here. It doesn't have to be on. It does not need to be engaged. I need auto thrust available. That means not MEL'd. That means not inhibited for the remainder of flight, because that is something we can do by pushing and holding the instinctive disconnect push button for 15 seconds. That will effectively get rid of my auto thrust system. So effectively, I got to have it available, and as long as it's available, I can have the protection of alpha floor, which remember is very much predictive. In the simulator, I validate and demonstrate the predictive nature of it by usually putting you in maybe like a flaps 2 configuration, 180 knots, and then just disconnecting everything, hand flying, putting a 30-degree bank and pulling a considerable amount of G's on the side stick, and before you know it, we're not necessarily too close to VLS at that point, but still, nonetheless, we get alpha floor to activate, and that's a good demonstration of that. So that's alpha floor, and then the last alpha we have is alpha max. Alpha max, which is what? The maximum attainable angle of attack that the ELACs will allow. the maximum attainable angle of attack that the elevator aileron computer is going to allow. We're going to talk more about the ELACs here in just a little bit, but that's effectively your alphas. So in total, remember there's 5 when we talk about normal law, G-load protection, roll, pitch, speed, alphas. The alphas have 3, max, floor, and prot. We talked first about prot, alpha, prot, max, and floor. And that's all in normal law. Now, how do you know that you're in normal law? Of course, we have the green equal signs on the attitude indicator. And I just want to share with you the green equal signs. They're not just there saying, hey, you're in normal law. I stick them right in front of your face. They're very much at all of the varying limits of the envelope that is established by the flight control computers, right? So when we pitch up to plus 30, or when we bank 67 degrees, or when we get to VMO and you see the green equal signs everywhere, that's a very good indicator that obviously we're in normal law. And of course from there, we're going to dive into normal law and the different modes. So I just want to talk to you about the modes of normal law. I'm going to erase this here quickly. For any of you, maybe you're taking notes. I'll give you a second to copy that down before I erase it. But I just want to share some things about the modes, because normal law, unlike the rest of the laws, has different modes: ground, flight, flare. And we're going to talk now about each one of those in detail. So the ground mode in normal law, as you can imagine, is active on the ground. And what exactly is that, and why do I need a ground mode? One of the notable things about ground mode is the fact that the side stick relationship is direct. So I want to talk to you now about the side stick for a second and the relationship of what is direct versus G-load versus roll rate, and this whole thing is going to tie right back into why we need it in the various modes from ground to flight to flare. For any of you that have flown anything other than an Airbus, which is all of you, because at some point I'm sure you flew a 172 or a Piper Warrior or something to that effect, you're probably well aware of the fact that when you grab that control column or that yoke and you pull aft on it, there's probably a cable or a pulley system that's moving the elevator or the aileron or the rudder proportionate to your rudder or your elevator or aileron input. And so just to give you some paralleling to this, like even in the Boeing, for example, if I move the column 50% deflection aft elevator input, effectively now my elevator is going to move proportionate to the deflection of the control column, which is 50%. That's not necessarily true in the 320 or in an Airbus product, because we do have something called, of course, an elevator aileron computer. And your side stick, which is what this horrible drawing is right here. I have a great side stick right here, actually, which is a model from Ben. Thank you, Ben. I'm putting it to good use. So the side stick here, when I pull the side stick, okay, or I push it or I roll with it or I do whatever I do, I'm actually sending a command to an elevator aileron computer, and namely ELAC2, because ELAC2 is the primary driver of the elevator. That's somewhat relevant and important because ELAC1 can also, yes, provide pitch control via the elevator, but it only has authority through the blue hydraulic system to run the elevator, contrary to ELAC2, which has green and yellow authority on the elevator. And effectively what I want to share with you here now is just to bring some clarity to this, is that my elevator is going to move proportionate to the command of the ELAC, which is not necessarily proportionate to the command of the side stick by means of displacement. Simply put, here's what that means, very simply put. If I take the side stick and I deflect it aft, say 50%, the ELAC takes that input and it interprets it as a positive G change request. So an aft input is a positive G change request, aka elevator nose up, and a forward input would be negative G change request, elevator nose down. So the 50% aft input might, by the ELAC, be interpreted as I want a plus 1.25 G change, which may mean that the elevator, in order to give you this G change, needs to deflect a total of 30%. And so what you can see is that because there's this intermediary here that's converting an actual input to a G-load command, the elevator may not actually move proportionate to the side stick. That's effectively what your G-load is. Now, your ailerons work the same way. It's roll rate. And all of this, by the way, I just want to share with you, can very much be demonstrated and validated in an airplane, or better yet in a sim. I'm not saying go do this in the plane, but you could certainly get in the sim and just go level flight, 5,000 feet, turn off all the automation, autopilot, everything, auto thrust, grab the thrust levers and just go to toga. Now, what you would expect in any other airplane is for the nose to very dramatically come up. You would expect a very dramatic nose up pitching tendency because ultimately the engines are mounted under the wing, and any jet, this is a universal aerodynamic principle, when I apply thrust to an underwing mounted aircraft, underwing engine mounted aircraft, then effectively that nose up tendency is going to be pretty aggressive. And this is basically what we call thrust vectoring, is the formal term for this in aerodynamics. But the 320, what you're going to notice in this example is that it actually doesn't pitch up very aggressively at all. In fact, it's quite the opposite. It's pretty anticlimactic. It doesn't really do anything. It kind of just maybe pitches a little bit, but then it settles. And the reason it settles is because the flight control computers are looking at your side stick, and the side stick input is nothing. And so because I'm not commanding anything, the ELAC says you want no G change, meaning no positive, no negative G. I don't want any pitching moment, but aerodynamically the thrust is causing that nose up tendency. So then the ELAC says you don't want any G change, and it actually begins applying input for you to not have the nose come up, which would be the natural tendency of the jet to bring the nose up if we didn't actually have this G-load roll rate flight control characteristic. So this, by the way, poses a big challenge for people later that transition to Boeing and we do stall recoveries, because you're so used to applying thrust in the recovery and not having a giant nose-up tendency, and then all of a sudden people are getting secondary stick shakers in the Boeing because it doesn't have this magic of G-load roll rate, right? And so why do I bring all this up? Well, because now we go back to the ground mode. And remember, the ground mode of normal law, as I was saying, one of the notable things about this is the fact that it's not G-load roll rate at all. It's direct. In other words, if your side stick input here is a 50% deflection, then literally what the elevator moves is 50%. Now, why is that way? And the reason it's that way really is two things. One, because I got to rotate the aircraft off the runway, and I can't pull more than 1 G's on a two-dimensional playing field, which is on planet Earth, right? So the ELAC doesn't understand positive G's on the ground because it can't pull any more than 1 G on the ground. And so in order to rotate off and give me a nose-up elevator deflection, I need a direct communication between side stick and elevator, right? So that's the first thing. The second thing, of course, is I got to do a flight control check, which we do usually on the taxi out, full up, down, neutral, left, right, neutral. And the only way for the elevator motion to happen is if I have a direct communication. Now I'm going to share something about the flight control check. Be very mindful that your flight control check, you're looking at the flight controls page, architecture, as Airbus puts it, when it pops up and you move that side stick, because yes, you do have the crosshair on the attitude indicator that will move. The crosshair being there is also a tall tale sign that you're in ground mode, because the crosshair disappears once we're airborne. We transition to flight mode, which we're going to look at. But the crosshair is tied to side stick input, and it is not tied to flight control surface deflection. So even though you might see the crosshair moving on the attitude indicator, you may actually not have any surface movement at all from your elevator or aileron input. So when you do your full up, down, neutral calls, make sure you're looking at the actual system's display page and not necessarily only the attitude indicator. So that's ground mode. Hopefully that makes sense. And of course, from ground mode, now we transition to flight mode. And flight mode is basically where the side stick characteristics change. And we go from a direct communication to now suddenly the G-load and the roll rate that you would expect in normal law in flight. The transition period is about 5 seconds. This is why the autopilot says don't engage it until approximately 5 seconds, 100 feet once we're airborne. It's going from ground mode to flight mode, as they like to call the blending. That blending process is the 5 second or 100-foot delay. And in flight mode, like we just covered, I do very much have G-load roll rate. The roll rate, similar to G-load, is not a direct communication, but it's a command to roll the aircraft at a rate proportionate to whatever you're commanding. And so a full side stick deflection is effectively 15 degrees per second. And I would also like to say on this note the fact that we do have something referred to as the algebraic summing of sidestick inputs. So what that simply means is that if I, let's say I'm the pilot flying, I grab the sidestick and I pull aft, and then the pilot monitoring for whatever reason grabs the sidestick and pushes forward, we're basically canceling each other out. And so the sum of that input is 0, and the jet will do nothing. It'll just continue flying straight and level. Same is true if one person goes full left or full right input and the other person goes full opposite input. The sum of both of those, of course, would be 0. That's kind of an interesting, unique design. I guess to some degree I like it, to some degree I don't. There's some questioning whether or not that was a contributing factor with Air France 447 because it was dark, nobody could see the input, so on and so forth. Yes, you can hear dual input, I get that. There's also, of course, the takeover push button that we can talk about. So whether it's good or bad is neither here nor there. It's just something you should be mindful of, that the sticks are summed, especially for those of you that are line check airmen or captains and you're kind of monitoring your first officer as they come in to land and maybe you need to make a correction. Be ready to hit the takeover push button because your input is going to be added or summed up to whatever their input is, which could quickly bring you to a tail strike scenario if you're both putting an input that would yield that result, right? So just something to be mindful of. The last thing I'll share with you is that we have flare mode. We got flare mode, and flare mode, if you don't know, only available in normal law. Basically, the ELAC takes a snapshot of your pitch attitude on the approach, and this is going to happen right at 50 feet. And as an example, I'm going to say your pitch attitude here is, say, a positive 4 degrees nose up. So plus 4 degrees nose up. It takes that picture right there, and then at 30 degrees, or 30 feet, I should say, at 30 feet, it begins applying a nose down pitching moment that you're going to counter with aft elevator input to make the landing flare seem natural and normal by comparison to any other jet you've landed. Now, why do we need this? So I want to turn your attention away from this for just a second, and I want to say, think about any other airplane you have flown that is not an Airbus, any of them, anything, from a 172 to a 747 that is not an Airbus. If you look and think about your landing flare, and you can just Google a YouTube video on cockpit 737 landing video, and you're going to see the inputs that are being done on this column. They're not one continuous aft input to a touchdown. They're generally an aft input followed by a neutral input to an aft input to a neutral input. And if you were to put a high-speed camera on the elevator back there, right, what you would see, of course, is the elevator deflecting nose up and then back to the neutral position, nose up, back to the neutral position, up and down like this. And so the reason you're having to continually apply this aft input is because you're, of course, trying to soften the landing because there's a natural tendency for the nose to want to come down as the elevator returns back to the neutral position. Well, we just learned that the side stick is actually commanding G load. And if you don't have an input, that effectively means no pitch change. So then think about this for a second, right? If you're coming up to the runway and you flare and you bring the nose up, and you're looking great, and you bring the nose up, and then you neutralize the side stick, and you don't put any input anymore. The ELAC interprets the lack of input as no G change. Translation, do not change the pitch attitude. So the nose will stay right where it is, and the elevator would actually still apply inputs to keep the nose right where it is. Even though you're not applying an input to the side stick, there would still be elevator motion technically on a small level to comply with your input or lack of input, right, which is no G change on the side stick. So that would lead to effectively like this endless floating scenario where the jet's basically just hovering there. And so the only reason we have to continually add this aft elevator input is because the flare mode is effectively taking the nose, and I like to think of it as like almost a rubber band that's just compressing the nose down towards the runway. And as it brings the nose down, I have no other option but to continually apply my aft elevator inputs, which is natural to the sensation I would have if I were landing any other airplane. So that's one of the dominant reasons why we have that flare mode in normal law. Hopefully this makes sense. And with that effectively covers the 3 different modes that we have. I don't see nothing in the chat. If you have questions, by all means, drop them in there, and we'll hopefully answer them as best as we can. In the meantime, we'll keep pressing through. Okay, so that is ground, flight, and flare mode in normal law. So now, we're going to degrade in laws now left to right, progressively, we're getting worse and worse here, right? So from normal law, we go to alternate law, and basically the way that we go to alternate law is by losing a system plus a redundancy. That's kind of the nutshell answer to this. I think, to me, that's the best answer. How do I lose, or how do I end up in alternate law? By losing a system plus a redundancy. You can give examples if asked, certain things like that in an oral, but for the purpose of this, that's kind of the universal answer. And how do you know you're in alternate law? Well, you have amber X's, that's the first thing. The second thing, you have an ECAM memo that will pop up and it'll say alternate law, protection lost. And I just want you to know amber X's are existent in alternate, in direct, in abnormal attitude, in mechanical backup, right? So if you're looking and you're saying, well, I must be in alternate law because I have amber X's. Well, possibly, but not necessarily. I think the better response, if ever asked in a training or checking scenario, what does amber X's mean? It means I'm not in normal law. I am not in normal law. I could be in any of these other different variations of a law or lack of a law altogether with mechanical backup. In alternate law, as far as protections, what do we have as far as protections? Well, we got G-load protection, and that's really about it. And then you have stabilities, something called stabilities. So I'm just going to list here, we have G-load protection, and then we have something called stabilities. Now, stabilities, I'm just going to abbreviate it, stabilities are not protections. Stabilities are recommendations. Why do I emphasize they're recommendations? Because they can be overridden. I can override a stability. I cannot override a protection, but I can very much override a stability. So the G-load we're clear on because we talked about it, but let's go to the stabilities. I have something referred to as high-speed stability, and then I have low-speed stability. High-speed stability is comparable to your high-speed protection, where it brings the nose up. The high-speed stability will very much give you that nose-up pitching moment, right? So we can start to reduce the airspeed. But the thing is, I can grab the Sidestick and just bury it forward, and there's nothing that it's going to actually do to prevent me from doing that, and I could very much overspeed the airplane. The low-speed stability is very similar in that as we approach a high angle of attack where we're approaching a stall, it'll suggest, that's kind of the word to use here, it'll recommend or it'll suggest that we lower the nose, and it will. It'll lower the nose for you, very subtly though. It's nothing crazy. It's just going to nudge the nose over, and when it does nudge the nose over, if you wanted to, you could grab the Sidestick and continue pulling aft, and you could very much override the low speed stability. So they are recommendations, they are not protections, they can be overridden, but they're also only available in alternate law, these stabilities that we're talking about. Typically, when we are in sim training and checking, and we do our stall recovery, we want to recover at the first indication of a stall. We do a series of 3 stalls. The first one's with the autopilot on. Recovery is initiated at the autopilot disconnection. That's the signaling of alpha prot. The second one that we do is in alternate law. We force the jet in alternate law, and we give you a bank, 20 degrees usually, 1,000 foot per minute climb, and the recovery is at the low speed stability. When you feel the nose pitching down, that's when we say stall, I have control, nose down pitch control apply, and then we level the wings, right? So big emphasis on lowering the nose, right, obviously. So that's your stabilities there. Let's see here. Why for landing in alternate law? Let me get through some of these maybe in the chat, hopefully. Why for landing in alternate law? In direct law, we can use only flap 3 config. I'm not aware that we can only use flaps 3. If we can, that's news to me. I don't know if that's something where you fly or if that's a legitimate Airbus thing. Or maybe I just haven't tried this and I haven't noticed it. What else we have here? How do you know you're in alternate law with or without the stabilities? There's no indication, Rick. That's it doesn't say you're with stabilities or without stabilities. I guess if you approach to where the stability would activate, you would know. But there's no direct indicator that I know of that says, hey, you do or do not actually have the stabilities. Neos behave a bit different in the flare mode. They do. The 321 Neo is kind of an interesting jet to land, in my opinion. Just my experience of it. Steven, my man, converting Airbus language to layman's terms. Well, we're trying. Trying to make it simple. We'll see how much we can actually simplify it. Okay, so, and then of course we have the G-load. Now the relationship as far as the side stick is concerned, is G-load, but then we have direct in the roll axis. So the side stick here, I still have the G-load, which gives me the protection, but the roll axis is very much direct. So you would expect that it's going to be a little bit more sensitive than what you would be used to, considering how it normally would feel in normal law. But this also, by the way, makes steep turns in alternate law easier, because in alternate law, we don't have something referred to as positive spiral stability. Positive spiral stability is basically if the jet exceeds 33 degrees of bank, it wants to roll you back. And so the whole time you're doing a steep turn, it's like you're fighting against this tendency for the jet to want to roll you back in normal law. Then all of a sudden you put it in alternate law, you do the same steep turn, and frankly it's easier, despite the fact that maybe it's a little bit more sensitive, but it's absolutely easier, in my opinion, in alternate law. So how do we know we're there? Amber X's. And we have the ECAM memo, we have the 1 protection, the 2 stabilities, and the slight variation in the side stick relationship. The next thing we have from alternate is direct. And what is direct law? It's what it sounds like. The side stick relationship is very much direct, everything in both pitch and roll. As far as protections here, what do we have? Not applicable, none. You're basically in a Boeing. You're in a non-protected jet, so to speak. And the reason dominantly that we have direct is because of the lack of the flare mode. So let's just talk for a moment about how do we actually get into direct law. So first you have to be an alternate. And then I have to place the gear down, but I additionally need to have the autopilot off. And this is a point that a lot of people tend to miss. For me to get to direct law, I've got to be an alternate, and then I go gear down with autopilot disconnected. If you have the autopilot on, and you put the gear down, and you're in alternate law, you actually stay in alternate law, and you would not go down or decay down to direct law until you disconnect the autopilot. Now, if you do a go-around, you're in direct law, you're coming in for the approach, go-around flaps, positive climb, gear up, you put the gear up. Do you stay in direct or do you go back to alternate? You very much go back to alternate, because the condition for alternate has now been removed, which is the gear needed to be down. So that's another, usually I find, a slight confusion point amongst people. If I put the gear back up, you do very much go back to alternate, which of course means you now have a variation in the side stick relationship again. So you went from direct back to G-load for pitch and direct for roll. And I want to share something with you quickly as I talk about the go-around. It just came to mind. In normal law, we have that flare mode. A lot of times in sim training, you do rejected landings. Rejected landings. So the rejected landing, by definition of the ACS, Airman Cert Standard, is basically that you got down to 50 feet and then you initiated the rejected landing, the go-around, right? So you get down to 50 feet, and the reason we always go down to 50 feet is for 2 things dominantly. On an initial type, I got to do 4 approaches, 2 precision, 2 non-precision. That's a total of 4. One of these landings can be counted if it is a rejected landing. So in other words, for me to count a landing as a landing, I have to be in position to land by 50 feet, speed, and in flare position. And assuming that's all true, if I initiate the go-around, one of these 4 could technically be counted as a landing. So they always bring you down to at least 50 feet and say go-around last moment. So they can count one of these as a landing for the purpose of the ACS. That's reason number 1. But reason number 2 now is because of the flare mode. Remember, the flare mode is applying this nose-down pitching moment. And when you apply the nose-down pitching moment, that jet is applying the nose-down pitching moment, and all of a sudden we do go-around flaps, it's a lot of aft stick input that's required to not only A, bring the nose up because you're going around, but B, you're trying to overcome the natural flare mode, bringing the nose down. So it's all this input, and you very well may be applying a considerable amount of stick input, and you're like, man, how come the nose isn't coming up as much as I would want? And then all of a sudden you hear positive climb, you command gear up, the gear comes up, the airplane realizes it's not landing, it cancels out the flare mode. All of a sudden the flare mode's no longer there. You have all of this aft side stick input, so you could quickly over rotate, exceed the flight director bar, which might lead to a speed decay potentially. Like that 50-foot rejected landing if you're mindful of all these things, it's usually not like a big deal, but it could turn into this thing where you have tons of aft input and then quickly are over controlling and then questioning, why am I over controlling so much? Well, you're not. I mean, it appears that you are, but you very much put the needed input to overcome the flare mode and get going, and then all of a sudden the flare mode released, and so now you have excessive input, so you're having to adjust that accordingly, right? So that's another reason that you'll see this in the sim quite a bit, is this rejected landing at 50 feet happening. Okay, so going back to that then, yeah, you very much have a direct communication between the side stick, and that's dominantly because you don't have the flare mode. So I don't have a flare mode, so now I have basically a 172 type approach to pitch and roll control. And then finally, we have abnormal attitude law. And abnormal attitude law, I will share with you, is, in my experience, the forgotten law. I think a lot of people forget this even exists. Some people call it abnormal alternate law. I've also seen it referred to as abnormal alternate law. I don't particularly like that. In the manual it says abnormal attitude law. That's how I emphasize we reference it. But abnormal attitude law is basically what it sounds like. This is where the jet has quickly exceeded the envelope, plus 30, right, 67 left, right. It's exceeded this envelope, and generally the roundabout way that I remember it is it's basically like a double of the envelope. If I go, say plus 60 nose high, it's really more than plus 50. But if I double the envelope, 67, if I double that, I go to 134 degrees. That's certainly more than 125, which is the value. I got to exceed 125 degrees of bank. If any of these are true, and there's no way to put the sim here, by the way, so I can't simulate it in a sim, but effectively the jet kind of throws its hands up and it says, I don't really know how I ended up here. Here, fix it. You have control, and it gives you control. And it doesn't hinder your ability to recover with any of the protections. It basically says, here, just fix it. And then once you finally fix it, it does kind of leave you in an alternate law with the G-load protection. So you do recover the G-load protection. There's been some discussion around this I will share, because early manuals of the 320 said in abnormal attitude law, and I have screenshots of this to validate it, basically that we do retain G-load protection, but the more recent versions of the manuals that I have seen say that the G-load is returned after we recover to a normal pitch attitude. So with that being said, I'm going to err on the side of the most recent revision I saw, which is basically that, hey, in abnormal attitude law, I don't have any protections, and then once I recover, then I retain G-load protection, and I'm going to stay in abnormal attitude law for the remainder of the flight. This is one of these laws. Now, I guess a lot of these decayed or degraded laws, or maybe some that you'll never see in your career, hopefully, but certainly abnormal attitude is one of the ones that I would hope you don't see. It's one of these that you have to get there not by a pilot input, because you couldn't get there by pilot input. This is like a mountain wave or wind shear, wake turbulence, or something disrupts you quickly, and all of a sudden you're kind of left to command the jet. I will say, if you find yourself in an abnormal attitude and you have this law active, for the moment that you don't have that G-load protection, it's imperative that you prioritize airspeed and not necessarily over G'ing. I would rather over speed than over G. This is kind of like an EET or UPRT 101 type lesson here that I'm giving you, but basically what it says is, I would rather overspeed a jet in an upset than over G it. Now ideally, obviously, we don't want to do either one, but because I don't have G-load protection, I certainly don't want to grab the side stick and yank a ton of G's on this, especially if I have a lot of airspeed. But we definitely have the VMO at a value that has a considerable buffer, and we can actually safely overspeed more than that in a very extreme, what's the word they use, egregious situation. So that's abnormal attitude law. And finally, the thing that I wrote up here on the far right is mechanical backup, that I'd like to talk a little bit about, shed some light on. And I think a good segue into that is to just put some attention on our computers, because our flight control computers are going to dictate basically how we end up getting to the mechanical backup as a whole. So we got ELAC 1 and 2. These are our two elevator aileron computers. Which ELAC dominantly drives the elevator? Let's see if somebody could say that. Which ELAC dominantly drives the elevator? Sec 1, Sec 2, Sec 3, and then we have FAC 1 and FAC 2. Okay, that should be what? 2, 4, 6, 7. Perfect. Those are my 7 computers. The dominant controller of my elevator. I don't think anyone answered that. Let me see. For a free trip to Hawaii and a brand new Mercedes. Someone's typing in there. ELAC 2 dominates the elevator most of the time. Juan Camilo for the win. Yes, sir. So ELAC 2 is mainly driving my elevator here. The beauty of ELAC 2 driving the elevator is that it also can do so with the green and the yellow hydraulic system. And then, of course, we have ELAC 1. That's the secondary means of driving the elevator, mainly by the blue system. Cool. And then we've got Sec 1, Sec 2, Sec 3, which I like to affectionately refer to as SC3. It's not that, but it's just, to me, it's spoiler computer because it doesn't actually do anything for me for the elevator. And then I have flight augmentation computer, which to me is the least intuitive of the 7, because this very much tells me elevator and aileron computer, and this tells me spoiler elevator computer, albeit Sec 3 should have just been spoiler computer. It's a little bit misleading. But flight augmentation, like what does that even mean, flight augmentation computer? So I like to affectionately refer to as the FAC, as the RAC, or the RAC. It is not that by definition, but it helps me remember what it does, which is rudder and angle of attack computer. Rudder and angle of attack computer. We'll talk about that here in just a second. Everything has to do mainly with rudder inputs dominantly. Okay, so which computers control the elevator? We have established that the elevator is dominantly controlled by ELAC 2 via green and yellow hydraulic. That's great. Let's say we've lost this computer, ELAC 2. It's going to now go to the secondary means of control, which is ELAC 1. Let's say we've lost ELAC number 1. So now, do we still retain elevator control? Of course we do, via the two SEC computers here, SEC 1 and 2. So now the question is, what happens if I lose these two? So I lose SEC 1, spoiler elevator control computer 1, and number 2. I have lost all 4 computers that have authority in the elevator. ELAC 1, 2, SEC 1 and 2 control the elevator. If I lose, here's the point, don't miss this one here. If I lose pitch control via the elevator, which would be these computers, I will end up in mechanical backup. This is how you get to mechanical backup. You lose control of the elevator. Now, usually when we talk about mechanical backup, and I say, hey, how do I get to mechanical backup? Everybody says, well, I lose all my flight control computers, which is not incorrect, because obviously if I lost all 7, that would include the 4. So not necessarily incorrect, but a more correct, more specific, more detailed response, in my opinion, would be to say, if I lose pitch control to the elevator via these 4 computers, that is going to place me in mechanical backup. Now, in mechanical backup, the means of which that I have to control the aircraft is basically the trim. So I'm controlling the stabilizer. And then I still have rudder input, which is great for yaw roll coupling. That's another aerodynamic term where basically a yaw input induces a roll. And I have thrust vectoring. So I have rudder, I have pitch trim, and I have thrust vectoring left-right to control the roll axes. That's how we get around in mechanical backup. Now, mechanical backup for the most part is there and designed to help you keep the blue side up, to keep flying, to stay flying, so that hopefully at some point somebody can do some kind of a reset that'll reestablish at least one of these computers. And if I can reestablish at least one of these computers and restore pitch control via the elevator here, then I will have ultimately regained a law, which would be alternate law, that would later turn to direct when we put the gear down with the autopilot off, so on and so forth, right? But mechanical backup, I just want you to know, is the absence of all laws. It's entered into when we lose pitch control to the elevator, which would translate into basically loss of one of these 4 computers. There's 3 ways to control the airplane in mechanical backup, with the objective not to be to land the jet necessarily like that, but just to reestablish one of these laws. RAC for Cody. Thank you, Chan Ki Kong. Rudder angle of attack control or computer. Rudder angle of attack computer. That's just how I remember what it does, by the way. That's not formally written in a book somewhere. That's written in Joe's book somewhere. Okay, hopefully this makes sense. Keep in mind, when you have mechanical backup, you're going to see man pitch trim only in red above the attitude indicator. That's different from what you would expect to see with direct law, which is use man pitch trim. So one says to use man pitch trim, but then mechanical backup says man pitch trim only. And this will very much be accompanied by, this is a level 3 ECAM warning, ding, 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 lots of flashing bells and horns and all kinds of oral alerts and what have you, all right? Okay, let's now talk then about the FAC, or the RAC, the Flight Augmentation Computer. What exactly does that mean as it relates to all these things? So the Flight Augmentation Computer does mainly everything that has to do with the yaw axis. And so with that, I'm going to put a Y here, and we're going to talk about things that have to do with the Y, or the yaw axis. And there's 4 elements to this. I have rudder trim. The FAC controls rudder trim. I have the travel limiter. What is the travel limiter? The travel limiter, as you can probably see and have seen on the flight control page, is basically these 2 brackets that look very much like this, that swing in and out depending upon your speed. Low speed, the brackets are wide open, giving you full deflection. And then, of course, high speed, the brackets will start to close up, giving you lesser deflection on the rudder, mainly so that we don't overstress the vertical stabilizer and the rudder surface as a whole. So that is your travel limiter. We have turn coordination. Turn coordination. And then lastly, we have yaw damping. Yaw damping. Damping, not dampening. We're not wetting anything. There's nothing being dampened. It's damping, yaw damping. So I got rudder trim, travel limiter, turn coordination. You'll notice I grouped the T's together because to me it's easier to remember this when I need to get it out in a checking environment. Trim, travel limiter, turn coordination, yaw damping. All things yaw axis related. This is coming from the FAC or the RAC, however you want to remember it. I have airspeed envelope. What is it? What airspeed envelope are you talking about, Joe? I'm talking about in normal law, characteristic speeds that you can read about. We have basically this presentation that's like a stack. I guess really you have it all kind of in line with each other, but divided up like this. So we've got VLS over here, lowest selectable speed. By the way, I just got an email, a question, somebody asking, you know, how come VLS on the tape look different than the VLS on the perf approach page? You know, so they're looking at the perf approach and they could see, you know, VLS is 135 or whatever. Then they look at the airspeed tape and they're like, yeah, but the number, you know, disagrees. Well, remember VLS on the tape, driven by the FAC, is dynamic, so it moves with flap, spoiler, and G loading. So, you know, it's possible that you were either in a turn, you were pulling some Gs, you had a flap configuration or the spoiler deploy, and the VLS is sliding up and down, and it will differ than what you see in the perf approach page, right? So, you know, one is FMGC calculated down there, but the other one is a presentation being displayed by the FAC. And so to that degree, I want to share something else with you, which is the fact that you also have alpha prot displayed here, which is kind of like this, you know, different dashed lines. And alpha prot, remember earlier I said that's the angle of attack where flight control computers intervene to prevent stall. It's not airspeed protection. It's not the airspeed where flight control computers intervene to prevent stall. It's the angle of attack where flight control computers intervene to prevent stall. So why do I say that? Because in initial, we do an alpha prot demonstration, and the demonstration takes us down into this range, this band of the airspeed tape, and you're there, you're sitting in it for a while, and you're seeing the speed trend down, and you're like, man, how come I'm in it? I'm in alpha prot, but the autopilot's not disconnecting, the spoilers aren't stowing, all these things you said are going to happen, they're not happening. Well, because this is an approximation. So the FAC gives me this airspeed envelope presentation with an approximate angle of attack where alpha prot's going to activate, but it's based on an AOA. So you may be sitting in alpha prot band for a while before it actually hits the angle of attack, even though it appears as though you're actually buried in it, and you're not quite yet. And then, of course, same is true for alpha max. It is also the angle of attack where the flight control computers intervene and prevent stall. So if you ever get there in a demo in a sim, you might be a little bit into it before the actual alpha max activation happens. Okay, so that's your airspeed envelope then as it relates to what the FAC gives us. And then we have wind shear alerts. That's another thing that the FAC likes to provide for us, fortunately. And then the last thing we have is the low energy warning. The low energy warning. All FAC provided. So we have the yaw inputs, the airspeed envelope, the wind shear alerts, and the low energy warning. The low energy warning, if you don't know, that's basically where you hear the speed. You're only going to get this on approach because the flaps have to be 2, 3, or full configuration. You get a little bit slow on the airspeed, and all of a sudden the airplane starts saying speed, speed, speed. Sometimes we hear this in the circling approach. Not frequently, but in the circling, you could get potentially the low energy warning because you're banking close to the ground. You're very slow. The VLS is creeping up on you. And another thing that could happen too in circling approaches is alpha floor activation. That's usually why they kind of recommend having selected speed until your circling maneuver is complete, and then when you're on the final approach course, managing it up so that you prevent that from happening. Can alpha max speed be higher than high angle of attack speed? Can alpha max be higher than... If I understand what you're asking, I think maybe what you're saying is it possible for alpha max to activate technically, despite the fact that I'm not even near the airspeed alpha max presentation? Yes, is to me the logical answer, because the speed presentation is only that. It is a presentation. So you could technically have reached alpha max, even though maybe the presentation didn't catch up truly with where the AOA actually is. And the activation of the protection is based on the AOA and not the speed. So yes would be the answer. That's what I would say to that. Okay, how are we doing? How long have I been talking here for a while? An hour? What do you think so far? We got a live viewer in the audience. Solid. Everything good? Really appreciate you guys being here. 39 people. Looks like this has been filling up more and more. That's awesome. All right, we talked about the flight control computers, the 7 of them: normal, alternate, direct, abnormal attitude, mechanical backup, ground, flight, and flare mode. The way these usually come, first of all, I would say do as much as you can to see this demonstrated in a sim. It really helps to see this stuff demonstrated in a sim. Unfortunately, a lot of times some of these things don't get demonstrated, but to see it in all practical application is a really good thing. Like, for example, the auto thrust. Okay, I just want to share a couple things about that are really good for you to see. The auto thrust very much has an active range, and this will tie back into, say, even alpha floor and how do I get out of it, and toga lock and all these things, right? So imagine for a moment that, this is your thrust levers here, your throttle quadrant, and this point is idle. Your auto thrust active range, 2 engines, is just above idle up to and including climb. So, in other words, if I bring the thrust levers here to idle, I'm out of the active range. Now, this would technically disconnect the autothrust. In fact, this is how we disconnect the autothrust all the time when we land. When the airplane says retard, retard, we grab the thrust levers, we retard them all the way back to idle. We don't really disconnect the autothrust. I mean, unless you've been hand flying, including no automation, no autothrust from way back on final. But on landing, it's not like I have to, let me flare and then idle and disconnect the autothrust at the same time, which is what we do in the Boeing, by the way. We have to disconnect it manually because reducing it to idle doesn't do anything for us, right? So, not to turn it to a Boeing class, but I'm just saying with you, I think it's a great feature that, hey, I bring it back to idle, it disconnects it for me because I'm technically out of the active range, and that's what we want to know here. Now, if I go just above idle up to and including climb, this is the active range for 2 engines, and what happens is, like on takeoff, for example, when we go to toga or flex, and you start to read the FMA, and the FMA says man flex. If I read it left to right, let's turn this into an FMA up here now, just for a second, for the sake of conversation. Auto thrust column far left, right? It'll say man flex, whatever, 56, man flex 56, SRS, runway, auto thrust blue. Something like that. Okay, so the man flex is what? Manual flex. What it really means is the thrust lever is here in the flex position, which is very much a manual position. The auto thrust has no authority, no jurisdiction. It's not going to reduce the thrust for you. It's not going to do any of that stuff, which is why, by the way, auto thrust is blue. Man flex, SRS runway auto thrust blue. The reason it's blue is because it's armed, it's not active, which would have made it white. And the reason it's not active is because it's out of the active range, which is why it reads manual. So then we get to the thrust reduction, we bring it back, we go to the climb position, and all of a sudden we see thrust, climb, climb, auto thrust turns to white, and the white very much means now it's active. Now, all this will tie back into what I'm going to say with alpha floor in a second. If I am single engine, then technically my active range goes up a little bit more to the flex MCT position, right? So for 1 engine, active range, I have just above idle up to and including flex MCT. In fact, if you don't move the thrust lever to flex MCT, the FMA gets upset and just starts flashing at you, lever climb, right? And then eventually, you can do this demo even with 2 engines. If you reduce the thrust back a little bit to say here, just below the climb, it'll spit this ECAM, right? And the ECAM will say, auto flight, auto thrust limited, thrust levers move. It's basically saying you're limiting my ability to give you a full range of auto thrust capability. So that's why I like to tell people, if the auto thrust is off, your thrust levers are thrust levers in all the traditional context of what you would expect a thrust lever to do. Reduce, it reduces, add, and it increases thrust. If auto thrust is on, then the thrust levers are not levers, but they're limiters. They are now thrust limiters, meaning wherever the thrust lever or limiter is placed, that's going to be the limit of how much the auto thrust has the range or the authority to give you thrust, which it doesn't like to be limited, which is why it'll spit an ECAM if you do end up limiting it at all. So now finally, let's go to toga. If I put up here the thrust levers in the toga position, the FMA will read man toga because yet again, you are in a manual thrust position and the auto thrust doesn't have any jurisdiction or authority up here, right? So, when I said earlier, alpha floor is a predictive function of auto thrust, and one of the ways that I can turn it off is by deselecting it, but then also I can bring the thrust levers back to idle. Well, why does that work? Because you're out of the active range. And the moment you do that in the idle perspective, not on the toga, but if you bring it out of the active range back to idle, then it will indeed disconnect alpha floor and get rid of toga lock. Now, when you go to put the thrust lever or the auto thrust back on, you engage the auto thrust push button and place the thrust levers into the climb position. And I just want you to understand too, remember your auto thrust system technically is a double channel system. It has 2 channels because the auto thrust system works with FMGC1 and FMGC2, even though there's a single push button. People mistake this too on an oral. How many auto thrust systems do we have? And people, well, there's one button. And even so there's 2 autopilot buttons. We have 2 autopilots, but there's 1 auto thrust button, so there's only 1 auto thrust system. There's actually a single button, but 2 different channels. And the channel that's being used is directly tied to the autopilot that's engaged, right? So if autopilot 1 is on, then FMGC 1 is powering auto thrust, and if autopilot 2 is commanding, then auto thrust is slave to FMGC number 2. And if no autopilot is on at all, then technically it is slave to and defaults to FMGC number 1. But it is very much a dual channel system, just a single auto thrust push button, which brings me to my next point, which is the fact that this auto thrust push button is not the way that we disconnect the auto thrust. In fact, doing so will give you a fault. And the fault that it'll give you is thrust lock. THR-LK. THR-LK thrust lock. And that means what it sounds like. The thrust will be locked at the last sensed value, whatever that happens to be. Because you have to understand, if you go deselect auto thrust on the FCU, the auto thrust system basically interprets that as an auto thrust channel failure. It interprets that as an auto thrust system failure. And anytime the auto thrust system fails, it defaults into locking the last sense thrust value. So that's why we get thrust lock in as an ECAM that'll pop up and say, hey, you have this condition. Now, ultimately to get out of here, it's really no big deal. You just move the thrust levers and you can go back and restore your auto thrust. What else did I not cover with the auto thrust? I guess another failure you can, not a failure, but another indication you could have is lever asym. So that obviously tells me that the thrust levers are asymmetrical. They're not married up together. So the auto thrust is full of different things in terms of alpha floor, alpha lock, toga lock, the protection, thrust lock, great many different things that from an oral perspective you can extract quite a few questions out of just this auto thrust system. All right, what other questions, if any, do we have on anything? I think for the laws we beat it up pretty good. The laws usually come when we hit the flight control computers. So when we go on the overhead panel, tell me a little bit about ELAC 1, SEC, FAC 1, what does it control, what does it drive, which SEC can only control the spoilers, that would be number 3. Okay, let's talk about the laws. What is it? What protections do we have? This kind of thing. I guess while I look at this, SRS, let me just shed some light on that for a moment. Speed reference system. And then Juan, I see your question up here. Great stuff. Thank you. Very good. Love it. Appreciate you all. Rajesh, good stuff. Appreciate you. Thank you, Yvonne. Thank you, Vishal. Thank you, Cody. Thank you, Chan. Mauricio, thank you very much. Joe, does it mean that if we are with alternate law, we need to turn off the autopilot before lowering the gear so that we can have direct law and actually land the airplane with direct input since we don't have the flare mode available? Meaning that we can't land the airplane with alternate law. Let me read it one more time quickly, but my initial response based on what I first read there is that the sequence doesn't matter. You can put the gear down and then turn the autopilot off, or you can turn the autopilot off and then put the gear down. Which one happens first that doesn't really matter. Yeah, no. Okay, so you can put the gear down first and delay the autopilot disconnection, and then at the last minute, then you can go ahead and disconnect the autopilot, and it'll still go to direct law, no problem. Just be ready for it's going to be sensitive. Less is more on the side stick. You can literally fly this with your fingertips. I mean, if you find yourself doing all kinds of input, you're working too hard, brother and sister. You got to let go of the stick, man. You got to just give me the light. Stephen Sean Paul in the building. Yes, sir. What is your ASAP acronym for Alpha Prod again? Man, I'm having fun with you guys here. ASAP. That's a song from a famous rapper, man. That's what ASAP is. For Alpha Prod, what is it? Angle of attack. So autopilot disconnects. Autopilot disconnects. Spoiler stow. Angle of attack is commanded by the side stick. Angle of attack commanded by the side stick. Pitch trim freezes. In the nose up direction. You still have nose down. Ben, I had slats completely locked one day. I had to land in direct law. Yikes. It was exactly as sensitive as in the sim. Wow, that's good to know. Yeah, fortunately, I've been flying the bus for 8 years, and I haven't been in direct law. I've never been in alternate law. I've had some interesting things happen, but we've always resolved it, so knock on wood, we haven't had anything too crazy. If the airplane lands in direct law, does that mean that there is no flare law? That's correct. No flare mode in direct law. You're out of luck, Philip. You're out of luck. Don't buy the Powerball ticket that day, brother. It's not going to work out for you, you know? You don't have any luck that day, man. What can I tell you? Or actually, maybe buy it, because the chances of you getting there is not too good. So maybe you got something on your side. Okay. Let's talk about SRS. I know this doesn't necessarily have to do with laws, but I'm having fun with you, and I find SRS to be one of these, I don't know, not too well understood things. Speed reference system. Stands for speed reference system. I guess that's a good starting point. SRS. There's two ways I can get to SRS, speed reference system. I got to be in toga, and that means I got to be either takeoff or go around. Takeoff or go around to get into speed reference system. Now, speed reference system basically means that the flight director bar is going to command an appropriate pitch attitude that would give me either, depending on if you're on takeoff or go around here, so it's going to give me V2 to V2 plus 10, obviously that's on takeoff, or it could give me VAP for a go around to VAP plus 10. Translation, 15 degrees nose up, roughly. Okay, and I'm going to say that with a big, roughly 15 degrees nose up. Now, most times we under-rotate on takeoff. V1, rotate, and we just pull a little bit aft. We wait for the jet to feel light, to pop off the ground, to start flying, and then once we're comfortable, we continue pulling, because the reality of it is everybody trains us that we got to rotate at 3 degrees per second. And I always laugh, and I find that a comical piece of instruction, because there's no way for me to measure 3 degrees per second. Other than, yes, the attitude indicator has pitch attitude degrees, and I could count to 5, and after 5 seconds I should in theory be at 15 degrees nose high. But there's no, what would be amazing, I think this would be great, is if we had like a little bar graph indicator like this, and as you pull aft on the stick, this just fills in. And then you could see, oh, I just got to pull until I reach the 3 degrees per second, and it'll just fill in all the way up to the 3 degrees. I think this would be a great addition too for rudder pressure with the V1 cut. How much rudder pressure do I need to add? Well, it depends on airspeed, and it depends on thrust output. And if we had a gauge like this that based on both of those variables would give me a bug, this is how much rudder you need, and then I can apply rudder input until I meet that or I match that indication, that'd be amazing. But we don't have that. So we're left to do some pilot stuff and do the stick and rudder game and figure it out on our own. And I'm going off on a tangent, but really what I'm trying to say here is that when we rotate at about 3 degrees per second, we're targeting about a positive 15 degrees nose up. Now the truth is, most rotations are delayed. We usually actually overshoot V2 to V2 plus 10 considerably, and we end up usually at like a V2 plus 20 at least, if not sometimes more, but generally it's like V2 plus 20 if you look at like FOQA data, if you can see that stuff. And so the result is the flight director bar goes kind of high, more than 15 degrees. It pitches up a little bit more assertively than that. And then everybody, No, you said it's going to go to 15 degrees, but actually it's up at 17 degrees. Yeah, it is temporarily. Remember, it's actually not pitching for a degrees of pitch. It's pitching for an approximate pitch attitude that would give you V2 to V2 plus 10, or VAP plus 10 as appropriate. And it's realized that you have exceeded the speed because you delayed the rotation a bit. So now it starts to pitch a little bit higher to bleed the speed. You're going to notice if you follow the flight director up, the speed starts to trend back and it bleeds off. And then when it bleeds off and it gets right back within that range of V2 to V2 plus 10, then the flight director bar starts to come down a little bit more and it meets you back towards that 15-degree mark. Now, that is all done automatically, and that's all true, assuming we're two engines. And then, of course, if we're single engine, then it's mainly pitching for V2, which is actually going to be roughly 12.5 degrees nose high. It's not targeting that per se, but it's targeting a speed, and it's going to happen to fall in line with basically that pitch attitude. So in terms of, when we're rotating and you have that over rotation, that's why it's pitching you up a bit aggressively, because it's trying to get you back inside of a speed window. Then, of course, you probably reached the thrust reduction acceleration altitude already, at which point the flight director bar now goes to 10 degrees to begin speeding up so you can begin cleaning up the airplane. So now all of this is out the window and we go into climb mode, and we're no longer in SRS anyways to begin with. So SRS, it stands for Speed Reference System. This is what it's pitching for, which is an approximate 15, and I just want you to know the way to get into this is I have to select either flex or toga for takeoff, and then when I'm in the air, to get the go around, I have to select toga with at least flaps 1 or greater. Gotta have flaps 1 or greater. This is why the no slat, no flap that we do in the sim, no slat, no flap approach and landing. The status page, when we get to status is status, right? Stop ECAM, checklist relay reset. No, okay, continue ECAM. And then it basically says set configuration 1 for landing, and it's like, yeah, but I don't have any flaps, so why do I put them in 1? Why? Because the only way to get SRS on a go around is to have flap 1. I got to be able to hit toga and have the flaps out. So it's really a matter of, you're actually not having the flaps out, you're having the flap handle. It's looking at the flap handle. I got to have them out so that the computer recognizes that SRS is prudent given the configuration that we're in. Yeah. Runway, of course, tells us that we have a localizer to track, and then finally auto thrust in blue. As I said earlier, if it is indeed blue, it's armed, white meaning active. Okay, that was a random whatever that was, but hopefully that made some good sense. What other questions we got? What do you guys want to know about? What do you want to talk about? We're making great time. Let me get some water. I stay hydrated, you know? What can I tell you? Let's see, if the airplane lands direct law, does that mean? Okay, that was the last one for Philip. Man, there's a lot we can talk about. I will share with you on October 29th and 30th, I'm going to be here for 2 days. I think it's a Wednesday, Thursday. Anyway, I'll be here both days talking about everything. Systems related, top to bottom, the overhead panel, top to bottom, left to right. Flight control laws, I'm going to go over them again, and then we're going to talk about automation. Talk about everything. Target speed during the soft go-around speed mode. As far as I know, Yvonne, it's the same. The target doesn't change as the speed. The thrust output does. I don't know if a speed changed. I do know of a thrust output change. Good question. What else? The live stream I did for the 7.3 was amazing. 2 days, 7 people there. Tons of like various backgrounds. Some people were GA, never flown anything bigger than a 172. That was very insightful to hear some of their questions. And then you have the people that are flying all over the world. Tons of experience. It was really cool to have that different ends of the spectrum. Doing the same thing as I said, October 29th, 30th. Hope to see you all there. Is the VAP to VAP plus 10 also the command the SRS gives you in a Windshear situation? So the initial pitch attitude is 17.5 in a Windshear, 17.5. is the pitch attitude initially, and then as needed to not have a radio altitude decreasing. And so let's talk about Windshear for just a second. I know there's other things that are coming in here. Windshear is one of these things that is not won by a function of airspeed, it's won by a function of angle of attack. So in other words, I won't spend a ton of time on this, but I just want you guys to be real clear on this. If this is your microburst, and you're coming up to it, and you get Windshear toga, and you start pitching into the flight director, and then it says if the flight director's not there, first of all, if the autopilot's engaged, leave it engaged. That's a beautiful thing about this machine. The autopilot fights the Windshear. It's great. Now, that doesn't mean sit on your hands, because it's very possible that the airspeed decays down to alpha prot, and when it does, one of the things of alpha prot is autopilot might disconnect, right? So now you're stuck, you're thrown into the fight, so to speak, right away. So now, when you're pitching, and first you go to the flight director bars, and if the flight director bars are not there, we go to initial pitch attitude of 17.5, which is roughly where they'd be waiting for you anyway. And the pilot monitoring, your role is pretty critical here, pilot monitoring. You're going to start calling off the radio altitude. You're going to say 500 feet climbing, 600 feet climbing, 700 climbing, 800 feet level, 800 descending, 700 descending, you're 700 level, 700 climbing. We're not calling it from the airspeed, from the altimeter, right? Because think about the definition of a wind shear, sudden change of wind direction and or speed over a short distance in the atmosphere, which means the pedostatic system is potentially erroneous, considering that what's swirling around the airplane outside is not stable air. So that's the first thing. That's why we're looking at the radio altitude, because it's very possible that it'll show the altimeter an erroneous climb or descent. And the other thing you'll notice is there's no mention of airspeed. So we don't say airspeed's low, airspeed's high. We don't say anything like that, because if you do hear speed is low, the tendency might be to lower the nose. And the only way to win the shear really is through angle of attack. So we're reliant on the protections to do what they need to do and allow us to just fly with aft side stick as needed to fight the shear. There's a really good video on YouTube. It's Delta 191. Delta 191. This was a L-1011 going into Dallas that crashed due to wind shear, unfortunately. When you listen to the cockpit recorder and you also see some of the inputs that were applied, there was some mention of airspeed. There was some nose-down pitch control inputs. Anyway, I won't get into the detail of it, but suffice it to say that the procedure, you'll notice, talks about RA, and it does not mention anything to do with airspeed, everything to do with vertical trend. Okay, let's see. I was hoping you were going to do something science with the gallon. Water hydration is good, though. Nothing science related, Natalie, unfortunately. I'm just, I would love to do some science demonstration, but I'm not that smart of an individual, so I just drink the water. Mauricio, could you walk me through when the yaw damper got jammed, talking about the facts and how it could be displayed on the eCam? Yaw damper jam. So I guess maybe what you're asking is on the flight control page. I don't know that if you have a jam yaw damper, would that spit an eCam out? I don't know. Maybe. The flight control page might dictate that. If you do have a stuck yaw damper, depending on how aggressive it is, obviously that could lead to a very bad situation. Remember, the yaw damper, really the primary thing with that is, does it have sufficient authority to cause a uncontrollable yaw roll tendency? Maybe. Differential thrust is what I would tell you. That's what you're going to need, is differential thrust. To control a rudder hard over, you're going to need differential thrust. US Air had a rudder hard over in the 7.3. I don't know if it was related to the yaw damper, but they definitely had a rudder hard over. And differential thrust is your friend in that case. On the flight control page, it might display it. I'm not sure. I'd have to look at that, but that's what I would expect. Let's see. When you have engine failure, why does the speed target stay at green dot and not accelerate to 250 knots? It climbs you at green dot. It climbs you at green dot, right? So when you reach the thrust reduction altitude and it flashes lever climb, and the acceleration altitude, which are usually coincident but not always, You put it in lever climb, and then all of a sudden it'll target green dot, because ultimately it's trying to keep you climbing at green dot. And then later on, you can accelerate if you want to accelerate, which is probably a decent idea to do so, but it just sets a speed target that's appropriate for the climb, which really, for you to climb and accelerate to 250 and have enough climb rate while you're accelerating, it's more realistic and probably ideal, and I would say to keep green dot. Is it fine to fly below the maneuver speed of the current config as long as it's above VLS? Is the maneuver speed a max speed where the maximum stick deflection can be achieved without load factor exceeding? As often the ATC speed will differ from the maneuver speed of a configuration, or is it better to fly the next configuration and fly above the maneuver speed of that configuration? I don't have any problem with flying a little bit below the configuration speed. You could technically go all the way down. That's the answer. Let me just simplify my answer and say technically yes. You could put it in flaps 1, not fly S speed, and go down to 170. I don't particularly do that. It brings me up, it sits the deck angle too high. It's uncomfortable. You're still going to have all the protections. You can still pull G's and everything. You'll have the protection. But you will probably more likely introduce alpha floor, because the configuration that you're in is such that it won't like the energy state given the configuration of the plane, as opposed to if I pull a little bit with flaps 1 versus with flaps 2, it's probably opening up an envelope as far as the alpha floor protection and when it would actually predict that I'm going to need toga power. So I would, in my opinion, Rajesh, I try to fly green dot clean. This is another thing. A lot of times I see people configuring, first they get to green dot, that's fine. Then they throw flaps 1, but then they don't slow. And then they just maintain the green dot speed with flaps 1. That's not very fuel efficient. So I don't really recommend doing that. If you're going to fly green dot, just fly green dot. And then when you start slowing, throw flaps 1, go down to S speed. If they say they give you like a reduced speed of 170, you go flaps 1. And then S speed is pretty much in the vicinity. It's pretty close. Could you technically go below that maneuvering speed of S speed down to 170? Yeah, sure. No problem. It's been done. People do it. It's not a problem. I would say, at least personally what I do, if I start slowing below that ideal speed for the configuration, then I'm mainly just looking at my pitch angle and then how far away is the VLS. And then some other variables would include, like, am I high? And are they going to dump me down? If all these are lining up where, yeah, you're kind of high, you're going to need to get down, then usually I'll just throw flaps 2, which will allow me to use the spoilers right away and not have the VLS shoot up to an uncomfortable position and potentially get closer to the alpha prot. So, kind of a long-winded answer. But yeah, you could fly below it and then monitor it. And then I would probably configure to the next flap setting if you're starting to get pretty far from the optimal. Soft go-around versus not soft go-around available, but selecting toga only momentarily. Always running the same because I've been told not to fly below S speed. Wasn't sure why. Some people come up with different things, Some of them I would say are justified and others are not. But the truth is you can go below it, no problem. People do it all the time. I would say for me, my favorite configurations in this plane are flaps 2, speed 170. This is really, really helpful from an energy management perspective. I don't know how many of you on here are relatively new to flying the 320, but I will share with you that, like any jet, the 320 is no exception to this. It does not go down and slow down very well. So as it relates to flap settings here that we're talking about, if you can imagine this is your runway, here's your final approach fix, and then here's your initial approach fix back here. I'm looking for a point, usually it's probably somewhere around the initial approach fix, that's 10 nautical miles away. And at 10 nautical miles away, that is going to be generally the point where I would like to be flaps 2, speed 170, maybe 180. Yes. People, oh, that's too conservative, Joe. I can push it. Yeah, of course you can. You can push it, right? But what I'm getting to is if you're roughly, as a rule of thumb, 10 miles out, 10 nautical miles out, flaps 2, you're in a good energy state to then later on drop the gear somewhere around 7 miles away, which is about 2,100 feet, and then be stable at 1,000 feet. So I always look on the chart and I'm like, okay, where's the point 10 miles away? So I can drop in flaps 2 somewhere around that point. The speed constraints that ATC gives almost always are 210 to 10, 170 to 5. 210 to 10 nautical miles and 170 to 5 nautical miles. If I can leave the airspeed managed all the way and just let it do it for me, including hit the decel point and start slowing and with the flap extension and all these things, perfect. I'd rather do that. It's less work for me. I'd rather just let the jet fly the way it was designed to fly. But if for some reason ATC's playing games, then, you know, we'll play games. 210 to 10 and 170 to 5, brother. Then we start throwing the flaps in there. Let's assume we depart heavy. Big discrepancy between V2 plus 10 and S speed. Heavy FATO. If there is a speed limitation on the first turn of EO SID, would you think selecting flaps 2 would be a better option if we depart with flaps 1? I would just get speed relief, to be honest. You could do that, but I would just tell ATC, we're heavy, unable to speed. Okay, speed your discretion. That's probably what's going to happen. I think that'd be easier to do than worry about the flaps. By the way, that happens a lot, especially here in Miami. Miami's full of freighters, 747s and MD-11s take off. They're super heavy, and there's speed constraints, and they can't comply with them for whatever reason, right? So they just get speed relief. But yeah, either way. I think either way is fine. I always teach flaps 2, the sweet spot for energy HC management. We got Shally in the studio. They want to see me?
You want to?
I'm good. Yeah. They're taking my lunch order. We're taking orders. Order me the anchovies pizza. I'm kidding. I don't eat that. Pepperoni? Huh? What are they ordering?
I have no idea.
Do you know what they're ordering? I don't know what they're ordering. What should we eat? Hawaiian pizza or pepperoni pizza? That's going to be a poll.
I think overwhelmingly pepperoni.
Pepperoni pizza? Either one, we can put it on our tray table, you know. We're not in a Boeing, guys. We got a table. Please explain again the difference between VLS and the MCDU and the one in the speed. Yeah, man. So the VLS on the VLS on the MCDU is basically a fixed number. So FMGC calculated, populates a number, right? So let's say it's 135. I'm just going to throw out some example number. Boom, there's my VLS there, lowest selectable speed. VLS is basically a function of stall speed. If I'm not mistaken, I think it's 1.3 times stall speed, I think is the number. Don't quote me on that, I gotta look it up. But it's 1.3 times the stall speed, I think is what it is. So anyway, so the point is that, let's say it's 135, right? So this is what you see in the perf approach page. But it doesn't account for really anything in terms of G-load that you're pulling or, you know, any configuration in your bank or anything like that, right? So then the FAC, the flight augmentation computer, remember earlier we said the FAC is controlling the airspeed envelope. It's giving that presentation of the airspeed envelope. And so that VLS presentation that you see there, you'll notice that if I have flaps 0, I put the spoilers out, VLS comes up. Then maybe I throw flaps 1, and then all of a sudden VLS starts to come down. Then I go flaps 2 and VLS comes down. But then maybe I put a bank in and I start to pull and add G-load, and then the VLS comes up. And so the VLS on the airspeed tape is variable with configuration and G-loading as far as what the airplane's feeling. That's not true for the VLS in the MCDU. If you look at the VLS in the MCDU, that number's fixed. So even as I'm moving the side stick and throwing flaps out and moving the spoiler, that number just stays there in that one calculated spot where the presentation is moving all up and down all over the place. So that's the difference, is the one that's pictured is fact generated and variable with configuration and G load, and the one that is in the MCDU is not, it's fixed. Juan Camilo. So the G-load arrow that I put at the start of this was basically I said, hey, we have G-load protection, 2.5 Gs plus 2.5 Gs to minus 1 G. And then I said that we have bank angle protection, 67-degree bank. And I said the reason it's 67 is because if you bank 67 and pull on the side stick to maintain altitude, that you would run up against the 2.5 G. Justin for the win. G load was related to the bank angle. Thanks for the great class. Thank you, Cody. Appreciate you, man. Appreciate you all. I got 2 students here with Diego in the classroom taking an oral. I'm going to go in there and tell them they both busted because they weren't in the live stream right now. You failed. Get out of here. No, I'm kidding. I'm sure they're doing great. They really are in there taking their oral right now. I'm sure they're doing amazing. Much of what I covered here today is on the video. In fact, all of it is. I'm doing a live stream again. I hope on the 29th and 30th. That's a whole day. That's 2 days. It's all day long. So if you can set aside the whole day, I guess it's going to be recorded also, I should say. So even if you can't be there live, then you can just watch the recording later on. I'm going to go through the overhead panel, the entire overhead panel. All of the fault lights, all of the systems, all of the probable questions, all the preferred responses. I'm going to talk about flight control laws again, and then I'm going to talk about automation. And I'm going to talk about the ECAM, the confusing ECAM, and the OEBs in red versus white, and what do we do at the status page, and when do we do computer reset, and the QRH, and then you go to the FCOM. And I got to tell you, the Airbus, I love this machine. I don't want to fly anything else. But by comparison to some other jets where you just do memory item and QRH, it can be, the procedures can be confusing, where it's like, do we have an OEB? And then, you know, no, we don't have an OEB. Okay, good. Is there a memory item? No, there's no memory item. Okay, does it analyze the ECAM? Does it make sense? Because it spits out ECAMs by level of priority and not anything logical other than what priority it thinks it is, level 1, 2, or 3. Then we go through the ECAM, then we get to status and stop ECAM, and we got to go through checklist relight reset, then we continue ECAM action complete. Now I got to go to the QRH. If it's not on the QRH, I got to go to the FCOM. If it's not on the FCOM, there's even a flight crew training manual. It's like, procedure's quite lengthy. I'm going to talk about all that in the live stream in detail, in depth. And what else am I going to talk about there, which is really important, the phases of the MCDU. That's another big one, 8 phases of the MCDU, which is basically pre-flight, takeoff, climb, cruise, descent, approach, go around, and done. Every time people say, what's it doing now? What's it doing now? The answer is always one of 2 things. It's in the FMA and you're just not reading it, or you don't understand the mode, or it has to do with the phase of the MCDU, something with the phase of the MCDU that you're in. One of those. Let's see, Joe's videos got me through ground, explode an airline, not exaggerating for those who are heading that way. Appreciate you, Justin. Really, really do. Arjun, same to you. Old fan, great to hear you live again. Really helped transition from 7.3. Appreciate you, Arjun. That was my story, man. I transitioned from 7.3 to 320, and I got to tell you, the first year that I flew the 320, I didn't like it. That's the bottom line. I didn't like the airplane. Mainly because I didn't understand the airplane, and worse yet, I didn't care to understand it. I didn't care to learn it. You got to understand, my dad worked for Boeing, okay? So I thought if I don't fly Boeing, he's going to disown my ass, okay? So I was not prepared to go fly an Airbus, and I was very much, if it's not Boeing, I'm not going. Now, that statement in today's day is somewhat questionable. I think people are saying if it is Boeing, I'm not going to some degree. Is this being recorded? Anyway, yeah, man. So, but what I will say though is that I've come to love the Airbus. I mean, I really have. But you got to embrace it. You got to want to learn it. And the beauty of this community is it's full of people that want to know more. They want to improve. They want to do better. You guys want to learn more. Otherwise, you wouldn't be here. Period. You just wouldn't be here if that wasn't the case, right? So, applause to you, and I got to congratulate you on that. Philip, to talk to you about. Steven, do your online courses follow the same format? Take my money. They do, Stephen. They do. They follow this format. Very simple, very digestible, very practical. I'm not a big theory guy. I don't like to sit and talk a lot of theory. I want practical application. This is true also for like the Train the Trainers course that I do. It's one of the programs that I love to deliver the most, AX3 instruction, basically how to be a more effective instructor. It's not fundamentals of instruction theory, rote memorization and correlation and all this good stuff. I've done enough of those FOI in my life. Usually I leave thinking that was cool, but it was all theory. Practical application. What can I go apply tomorrow in a classroom? The same is true for the videos for the systems. What can you go apply in the airplane live right now that could potentially make for a more efficient, safer flight for you and your passengers? Okay, so real quick, Phil, because I did see your comment about the normal law flight modes. There's ground, there's flight, there's flare. Ground mode, flight mode, flare mode. Ground mode, flight mode, flare mode. Ground mode is what it sounds like. It's when you're on the ground, got to have the engines running. You will know that you are there dominantly by A, you're obviously on the ground, but B, the attitude indicator will have right angles like this. And those right angles, along with the crosshair, is the limits of the side stick deflection, full aft, right? Full up, down, neutral, full left, right, neutral. When you see that presentation on the attitude indicator, you'll also see the green equal signs here, and of course you're going to have your engines running and you're on the ground. You know you're in ground mode. The significance of ground mode is that the flight control relationship is direct. And the reason that's relevant is because remember, in flight I have G load and roll rate, and I can't pull G's if I'm in the air, or if I'm on the ground. So in order to deflect the elevator up and down, I need a direct communication between the side stick and the elevator. I also need that direct communication to do a proper flight control check. So that's your ground mode. Once you get airborne, 5 seconds elapse, these right angles disappear. The right angles actually go away immediately upon LGCIU detecting weight off wheels. And then the crosshair goes away, and 5 seconds later I go to G-load roll rate on the side stick. That's what it's commanding. And that's flight mode. Flight mode gives me G-load. The dominant characteristic of flight mode is that the side stick relationship changes to G-load and roll rate, and that is what allows you to have G-load protection, one of the variables, right? And that's also the reason, though, because you have G-load, that you need the following mode, which is flare mode. So flight mode is characterized by G-load roll rate, and the flare mode is there as a result of having flight mode. And flare mode is where the airplane at 50 feet takes a picture of the pitch attitude so that at 30 feet it can begin applying the nose down pitching moment that allows you to begin to apply the aft input to counter the nose down pitching tendency that will ultimately lead to it feeling like a normal flare and landing. It starts at 30 feet because if you read the flight crew training manual, at 30 feet something else happens, which is it commands us to reduce the thrust to idle. Retard. So that's when the thrust gets reduced. That's when the flare formally gets initiated. and then your flare should take all of about 7 seconds, right? So the flare is about a 7-second thing. And that's relevant too because the flare mode, by the way, is active for 8 seconds, right? So at 30 feet, the nose down pitching moment happens, and it's taken that saved or stored pitch attitude and applying -2 degrees to it. So if your pitch attitude was +5 degrees, you're going to go down to +3 degrees, which is effectively 5 minus 2, right? It's going to take you to 3 degrees, and it's going to do that over a period of 8 seconds. And then that's why your aft input is going to become a necessity for you to flare. That's kind of the recap of the modes. All these modes are really only available in normal law. And in alternate law, you don't have this, flare mode, which is why when you put the gear down, you go to direct. so that we're not landing in G-load, but we're landing in a direct relationship, which models more closely to what you've always had in any other airplane that is not an Airbus product, so that you can land more accurately, or at least have it feel more natural. If it gets me the schedule, I'm going. Yeah, man, so look, the live stream is like this. All the training here is like this, guys. I mean, if you come do a type rating, we are a type rating center. A lot of people don't know that, but we very much are. You can come get a type here. You can come do anything you want here, really, including not get a type, but you just want to come in person and train with us. Nowadays, I find myself doing more admin work than instruction, so doing something like this is amazing. I love getting on a camera with this or even in front of a class, but everybody here really, I would say, is top-notch. They very much are looking out for you. They want the best for you. The live stream will very much be me, 2 days. Juan's probably going to pop in at some point and talk some things there as well, but it's very much this format, interactive. You'll have a camera yourself, so you'll be able to be on screen if you want to be on screen talking, asking questions. It's happening the 29th and 30th. The link for that is onestepprep.com/live, I think is the link for that. Yeah, onestepprep.com/live. Go sign up there. There's a coupon code because it is a paid thing, but if you use FL320, actually you can use that site-wide. FL320 takes 10% off everything on our website, FL320. Part of our collaboration with Flight Level 320. You can use that coupon code and get 10% off everything on onestepprep.com, including the live stream. And if you want to come do a type, then I'll be here waiting for you. If you want to do a 7-3 type, same. I'll probably at some point be your instructor or definitely your examiner because I'm the examiner on the 7-3 here for the moment. What happens if you float more than 8 seconds? The airplane will stop the pitch down movement. You're probably not gonna. Yeah, I mean you'll have a. If you float longer than, the flare mode is basically done after the end of 8 seconds. I think if you've retarded the thrust levers,